Okay, so imagine you've got electricity that's worth practically nothing. Energy that power plants literally have to throw away because the grid just can't take it. Now, what if there was a mathematical formula that could turn that wasted energy into something the global market pays top dollar for? Well, today we are diving into a research paper that proves this formula doesn't just exist, it's a fundamental, unchangeable feature of our economy.
Right. And this isn't some thought experiment. It's the core paradox this paper actually solves. The authors prove that this transformation from, zero to hero isn't just a lucky break. It's what they call a structural invariant, a predictable, totally baked-in feature of our energy and computing markets.
So here's how we're going to break it all down. First, we'll tackle this zero-to-hero paradox and what the paper calls stranded electrons. Then we'll get into the good stuff, the phi multiplier. That's the magic formula. We'll cover the 4 axioms that make it work, the powerhouse theorem of intertemporal synergy that proves the financial logic, and then we'll wrap up with a super practical 1-hour viability test you can actually use.
All right, Section 1, stranded electrons. See, to really get the hero, you have to start with the zero, and we're talking about structurally surplus energy, basically power that gets generated but has absolutely nowhere to go, which means its value drops to almost nothing.
And get this. In 2024 alone, the Iberian Peninsula had over 770 hours of what's called curtailment. That's really just a fancy way of saying that power operators were forced to just waste perfectly good wind and hydro energy because the grid was full. That is more than 32 straight days of wasted power. These are the stranded electrons we're talking about.
Now, the old school solution is just to build more power lines, but that costs a fortune. We're talking huge capital expenditure, and it can take a decade. This paper asks a much smarter question. Instead of solving the location problem by moving the electrons, what if we solve the value problem by transforming them right where they are?
And that question, that's what changes everything. It completely reframes the whole issue from a simple logistics headache into a massive value creation opportunity. And it leads us right to the paper's central discovery. Which brings us to Section 2, the phi multiplier. This is the economic engine at the absolute heart of this whole framework, a concept called the gross value multiplier, which is represented by the Greek letter phi. So put simply, phi just measures how many times more valuable an electron becomes when you use it to power a GPU for AI computing compared to just, selling it to the local grid. It's a ratio, a straight-up measure of value amplification. And this right here is the critical insight. The global market for AI compute, it couldn't care less where the electricity came from. It pays for the output, the bits. But the price for that surplus electricity, that's set locally, and it's often near zero. The phi multiplier is simply capturing the massive opportunity in that price gap. And believe me, this isn't just a theory. The researchers tested this phi multiplier across 5 totally different energy domains. And just look at these numbers. Whether it's hydro in Iberia, geothermal in Iceland, or even industrial waste heat, the value multiplier is consistently over 20 times. This is not an isolated effect.
So this data confirms the core finding. The phi multiplier isn't some accident. It is a structural invariant of the market. It holds up across dozens of different energy and hardware combinations. So you might be asking, what are the exact conditions you need to unlock this thing?
Well, that brings us to Section 3, the 4 axioms. The paper breaks this whole effect down into 4 simple, verifiable conditions. If a project meets these 4 rules, the phi multiplier effect is basically guaranteed. Let's just walk through them real quick. First, Axiom 1. The input energy has to be surplus, meaning its acquisition cost is pretty much zero. Second, Axiom 2. The system has to create at least 2 separate valuable things, like AI compute and, say, heat for a greenhouse. They call this co-production. Third, Axiom 3. The main energy infrastructure, like a dam, has to already exist. You're not building it from scratch. And finally, Axiom 4. The value of what you're making, in this case AI compute, has to be on a long-term growth trend. You get those 4 right, and the math just works. And this logical framework leads us straight to Section 4, and really the mathematical heart of the paper, the intertemporal synergy theorem, or IST. This is what elevates the idea from just a smart observation to a provable mathematical certainty. Yeah, I know. It sounds super complex, but let's just translate the math into what it actually means for business and for investment strategy, because the implications here are, well, they're profound. The IST gives us 3 game-changing insights. First, for any project that meets those 4 axioms, its financial value will grow faster than the cost of the money you'd borrow to build it. Second, and this is so important, delaying the project is mathematically expensive. The cost of waiting literally gets worse every single year. And third, they proved it. They used a real-world case study at the Miranda de Douro Dam in Portugal, which showed a synergy value over 30 times what was needed just to break even.
And this is just a powerful way of reframing risk, isn't it? The theorem isn't just pointing out an opportunity. It's quantifying the cost of doing nothing. In this model, the biggest financial risk isn't acting and maybe getting it wrong. It's waiting while the opportunity costs just compound against you.
Okay, so how can we actually apply this rigorous framework in the real world? Well, the paper gives us a simple, 2-step screening tool that turns all this complex theory into an actionable playbook.
It's a really straightforward 2-step process. Step 1 is a quick 15-minute qualitative check. Does the site meet the 4 axioms we just talked about? If the answer is yes, you move to Step 2, a 1-hour quantitative check to calculate the phi multiplier. And the paper proves that if phi is 10 times or greater, you've got yourself a viable candidate for deployment.
And this just shows you how incredibly resilient the model is. For that Miranda de Douro site, the analysis shows it only needs its computers to be running or occupied about 3.8% of the time to be profitable. Now compare that to a typical data center that needs to be around 85% full. That is a massive, massive margin of safety.
So this number on the screen, the calibrated synergy coefficient, it quantifies the total system synergy. For the Miranda de Douro project, it was 30.9. What that means is, at the moment of launch, the total value created by the combined system producing both electricity and AI compute was nearly 31 times greater than the value of just selling the energy to the grid by itself.
So let's just quickly recap the crucial points from this explainer. We've got a structural multiplier, phi, that consistently delivers a 20-fold or more increase in value. We have 4 simple axioms to identify these opportunities. We have a mathematical theorem that proves the biggest risk is actually delay. And we have a real-world validation showing a synergy coefficient of nearly 31. This paper lays out an incredibly compelling case, right? It establishes the mathematical foundation for this whole new economic engine. It proves that we're not just chasing some fleeting opportunity, but we're actually exploring a structural invariant of the global compute market. The science is done. The challenge now is all about execution and speed.